Welcome everyone to the Introduction to Statistics in R workshop presented by the Data Science Program of the Government of Manitoba. I'm Angela Kulamage, co-chair of programs for IPAT Manitoba, which is located on ancestral lands of the Anishinaabe, Ininewek, Anishinaabe, Dakota, and Dene, and on the homeland of the Métis. We acknowledge the distinct histories of the 7 numbered treaties that apply on this land. We recognize that public administration and public policy have been used as tools of colonialism and the harm this has caused to Indigenous people. We are committed to promoting public administration in a way that advances reconciliation in a spirit of collaboration with Indigenous people and communities. And on behalf of IPAT Manitoba and all of you gathered here, I would like to thank the Data Science Program and Matthew Cook, Senior Data Scientist in the Government of Manitoba's Data Science Program, based in the Department of Labour, Consumer Protection and Government Services. He's currently finishing his PhD in the Brain and Cognitive Sciences area in the Department of Psychology at the University of Manitoba, where he has taught R workshops to undergraduates, graduates, and faculty. So without further ado, over to you, Matt, and thank you.
Thank you very much. I'll just share my screen here. Okay, well, thanks for everyone for joining us today. So as Angela said, this is an Introduction to Statistics in R workshop. And, I just want to start by kind of talking about stats a little bit and kind of motivating what we're going to do here and what we're not going to do. So, for most of us, statistics, might sometimes just seem like a necessary evil, right? It's something you have to do if you want to get a paper published, or maybe there's some people in your department who are quite keen on stats and want you to run particular tests. But it's not always clear exactly why we need to run these tests. So I want to start kind of with these some interesting little allusions here to kind of illustrate the point and to emphasize why we really need statistics. So if you look at this little picture on the left here with these 2 monsters here, most of us, when we look at this, we'll see this bigger monster chasing a smaller monster down the hallway. But if you printed this image out and you actually took a ruler or a measuring tape and you measured the size of these monsters, there's not actually one larger one behind chasing a smaller one. They're actually identical sizes, right? And if you Google monster illusion after, you can put this into paint and move these around and see that that's true. But for most of us, when we look at this, that's not what we see, even though that's actually what's there. In this middle picture here with this checkerboard and the cylinder, you see these 2 tiles marked A and B. And again, for most of us, when we look at this, tile A looks a lot darker than tile B, but they're actually the exact same lightness and darkness. And here, I'll just quickly prove this to us here. So if we, let's just zoom in. So, tiles A and B look very, very different. If I select out and copy this out here, and I slowly move this over, we can see that even though it doesn't look like it when they're far apart, tile A and tile B are the exact same colors. Now, why do I bring this up? Why am I starting a statistics in R workshop with visual illusions? Well, I would argue that in the same way that we have visual illusions, we have statistical illusions. So, this is a plot that all of us are very familiar with. We have 2 bars that show, the average health for these 2 groups, A and B. And most of us, when we look at this, will say, well, group B has a higher amount of health on average. Maybe these are people that got some sort of treatment or whatever it is. But just like with the visual illusions, we can be fooled by sort of first impressions, right? And what we need to really understand this data are particular tools. So in the same way, we need a tape measure or a ruler to understand what's going on in this first little diagram here to see that these 2 monsters are indeed the same height. Or we need tools and measurement tools from color theory to know that these 2 squares, have the same hue, value, or saturation. In the same way, to understand data, we need the tools of statistics to actually be able to look at this data. And rather than just looking at it visually and saying that, well, it seems like group B has better health, we need the tools of statistics to incorporate in understanding and measurements of randomness and probability so that we can get a better sense of whether these groups are actually different or not. So that's what statistics is really about, it's really just giving us a tool to better understand data. And there are a couple ways, before we jump in, the one thing I'll say is, there's a couple ways of understanding statistics and trying to learn it. The first is sort of the conceptual, and that's what, if you were there for our thinking with data presentation, that's what that presentation was all about, is really the conceptual understanding of, well, how do you measure relationships in data? What is a correlation? What is a p-value? How does sample size determine, maybe what test to use or how to interpret certain tests? So that's one aspect, and we're going to be talking about that conceptual aspect today. There's another aspect too that we're not really going to be talking about, which is the mathematical aspect, right? So if I give you some raw data, can you take that data and plug it into some formulas to get out the required values from these tests? And we'll talk about that briefly, but we're not going to really be going through the mathematics. And the reason for that is that unless you're very comfortable with mathematics, looking at the formula for a correlation or a t-test or an ANOVA is not probably going to give you a lot of insight into what that test is doing. And then the third sort of component, which we're going to be spending a lot of time on, is the practical aspect or the applied aspect of, given that you have some data, how can we use a program like R or Python or SPSS or SAS or Stata to actually do that test, be it an ANOVA or a regression or what have you. I'm just going to make my font just a little bit larger for all of you here. So we're mainly going to focus today, like I said, on the practical aspect and the conceptual aspect. So what I'm going to do here is just open up an R script. So right under File there, if you click that little button that has the little green plus, we'll get a new R script here. So the first thing I'm going to do, some data was sent around to everyone. If you don't have that data, if you email manitoba@ipac.ca, Angela can just forward you that data. But to get started, what I'm going to do is kind of start the way we always start these. I'm going to load in a library called Tidyverse, and this is just a set of packages that we use for data manipulation and visualization. So I'll just highlight that and click Control Enter. It'll take a couple seconds, but it'll load up all the packages we're going to need. So the first thing we're going to want to do is get this data into R. So unlike some of the other workshops where we use some data that was built into R, I generated some fake data that will really help emphasize the points that we're trying to make and things that we want to look at. So just on my file explorer here, so you should have this zip file, this data file, downloaded somewhere on your computer. It doesn't really matter where you have it, but the first thing we just need to do is unzip it or extract it or uncompress it so that we can get out these data files you see in here. There are 10 data files. So what I'm going to do is just right click and click Open with WinZip, or you could just double click it. And I'm just going to just click yes, unzip to wherever I have it saved. Like I said, it doesn't really matter where you have these files saved on your computer. We'll pull these in from wherever you have it fairly easily. So I have this just in a folder in my computer, but now you see, in addition to this zip file here, I have an uncompressed regular folder. And if I go inside of there, I have all my files. So that's all you need to be able to do. And of course, you can just click on these and look at them too. We'll open them up in R, but you could open them up in Excel and see that they're nothing too fancy. This first one just has a column of numbers. So I'll go back to R now that we have those opened up, and what we're going to do is read these data in. So we'll read in data set 1, and I'm going to just call this data 1. You could call this whatever you want, but I'm calling it data 1 just to go along with the names. And I'm using this function called read CSV to read in this data file. And we could here type, where this data lives on our computer. I could say, data1.csv, but because all of us have likely saved this file to different places on our computers, this is going to cause a whole bunch of problems for me telling you where to look since I don't know where it is. So what we're going to do instead is just use this function that's really nice called file.choose. So when we put that inside of this read.csv function, what this is going to do when we run this is it's going to open up our file explorer. And you might see what happened to me here. It sort of was hidden. So if I just click this, it's going to open this up. And if I go to the location where I have this file, these files saved, I can go ahead and just select the one I want. So, if this was in your download folders or whatever it was, you can just go there. And if you see this, this uncompressed go inside that folder, you can just select any data that you want. So we're going to select this first one, data_01. And when I click open, you'll see here it's red in the data. And if we look on the right-hand side in this environment, now I have data loaded in. And if you save this as something different, it's just data or my data or whatever it is, you should see that on the right-hand side here as well. Now, this isn't something that I really recommend as a long-term solution, but for just sort of iterative and interactive work, it can be a good way to quickly read in a file. So just like we did with Excel, we can just click on this data1 and take a look at what we have here. And this is kind of small on my screen, but maybe what I'll do is down here, just type in data1 and we can see what we're working with. So we have a table with 50 rows and 1 column. And we see here we have IMDb ratings, and they look like they're from probably 1 to 10 or something like that. So the first statistical test we can use is the one everyone kind of learns about at the beginning of statistics, and it's called a t-test. And more specifically, it's called the one-sample t-test. And what this test essentially does is it lets us take in a set of numbers like these 50 movie ratings, and it lets us compare that average to some known average. So this is something that's quite common in something like medical testing. If doctors know that, the average resting heart rate in a population is whatever, I'm just going to make up a number, 70. And then there's some subpopulation, maybe people with a particular disorder, or maybe these are extreme athletes or whatever it is. And you collect that average resting heart rate from that group of people, from that group of athletes or whatever it is. What you want to do is compare that average to that known population average of 70, say, and see if it's different enough for it to be meaningful, right? I'm going to just use the phrase different from chance. So we'll talk about this more as we go, but let's see how we would do this. So the first thing we could do here is visualize the data. And this is something that's always good to do. So what I'm going to do is I'm just going to take data1, and this will just kind of be a bit of a refresher from the data visualization. But what we can do is say that what we want to do is plot this IMDb rating, and we're going to say we want a histogram. If I run this, it's going to give us a histogram here. So now we can visualize our data, right? So I'll just go ahead and open this up here. So what we have here, and it's a little small on the y-axis, but that's okay. So what we have here is we have our ratings, 4, 5, 6, 7, 8, and 9. So no one, rated these movies less than a 4 or more than a 9. And we can see the number of times people rated these. So the most common was 7. Maybe it looks like 15 or so people rated it 7, less people rated it 8. Not many people thought these movies were very low, right? So now what we want to do is essentially look to see what the average rating for this data set is. So we know how to do that if you remember, and if you don't remember, that's okay. What we can do is say we want to summarize mean IMDb rating. If we do that, we can see that the average rating for these 50 movies was 7.38, right? So let's say that we knew, for argument's sake, that the average IMDb rating for all the movies, all the millions of movies that are out there, is precisely 7. So now what we have is we have this unique little sample that we've collected, and maybe these are movies from a particular director or from a particular country, or maybe these are your favorite movies. And what we want to know is that 7.38 average rating for the sample we collected different than 7? Now, obviously, in the most naive, sort of simple way, the answer is, well, of course, right? 7.38, of course, that's different than 7. We don't need statistics to know that. But what the statistical test is going to tell us is 7.38 different enough from 7 that when we incorporate chance into that measurement, basically, is it different enough from 7 that can't be attributed merely to chance? right? If we plucked out a whole bunch of movies randomly, we might get 7.38 merely by chance. And this, if you remember from the thinking with data presentation, this comes back to this whole discussion that we talked about here, where we're looking at something like this, that if we sampled from a population with a known parameter, or if we sampled from all the movies from IMDb a whole bunch of times and calculated the average, we would get, most of the time we would get an average of 7, but sometimes we would get a little bit less or sometimes a little bit more. But how often would we ever see a sample of 50 movies that was this large or larger than 7? So that's kind of what we're doing. And when we see the test, we'll be able to look at these numbers more concretely. It's a little abstract right now. So what we're going to do this t-test is we're going to use this function called t.test. And what we're going to do is give it the set of ratings. So we'll write this out and then we can kind of quickly talk about this here. Data 1. Just type this out and we'll look at it. So what we have here is this function called t-test. We have to use this sort of syntax here where what we have is we're saying we're using data 1, and this $ just allows us to pull out this particular variable. So if we run just this, we'll see that what it gives us is these 50 IMDb ratings. And then we need to specify what they call mu. And what that is mu is the Greek letter for the population mean. So basically what this test is going to do is it's going to say, is this data statistically significantly different than 7? And if we run this, we'll see we get a lot of different information. But now we'll be able to talk about things a little bit more concretely. So it shows us what we ran here. It reminds us we're doing a 1 sample t-test. It reminds us what data we're using here. And then it gives us a couple pieces of information that are useful to us. We'll talk about those in just a second. But right at the bottom here, it actually shows us what we already knew. So it just reminds us that the average of this data is 7.38. And if we scroll up here, we can see that that's the exact same thing we calculated. And then here it will tell us that the alternative hypothesis, the thing that it's really testing is this mean different than 7? And the main thing we're going to look at to determine this is this p-value here. So the way that we're going to interpret this is actually quite straightforward. We talked about this at the Thinking with Data presentation. But the way that we interpret this is that if these 50 numbers came from a distribution that had an average rating of 7, we would only expect to see an average in our data that's 7.38 or more extreme, 0.03564% of the time, right? Now, what I said isn't quite true. Really what we're looking at is it larger than 0.38 or less than 0.38 away from 7? So really what we're looking at here is, what would that be? So really what this is telling us is that we would only expect to see a value less than 6.62 or greater than 7.38 about 3% of the time. Now, if we go back to this discussion that we looked at here, what we want to see, what we really want to see is this number as small as possible, right? What that would tell us is that the probability of observing the data we did, given the null hypothesis, given that there are no differences or that there's no, that the true population actually is 7, we would only expect to see those differences about 3% of the time. Now we'll see some examples, you know, if that's a little bit fuzzy, we'll see some we'll keep going through examples and see, and we'll build our intuition. But if that's not, you know, completely straightforward, I recommend going to that Thinking with Data presentation so that we can get a better sense of that. But that's the way that we interpret that. In short, is that the probability of observing data this extreme or more extreme, given that the true population IMDb rating is 7. We would only expect to see that about 3% of the time. So like I said, we'll go through some different examples and build our intuition, but that's how a one sample t-test really works. And to build our intuition maybe a little bit more, what we'll do is, let's say that we knew that the true population average was exactly the average we observed in our data, right? So what we want to know is 7.38 statistically different than 7.38, right? Now we sort of intuitively know the answer is going to be no, right? So if we run this, we can see that the p-value we get is 1. And the reason for that is that the probability of observing this data, given true data that has an average of 7.38, is extremely likely, right? If I told you that the average IMDb rating was 7.38, and I told you I collected data that had an average of 7.38, and I said, how surprising is that to you? You would say that's not surprising at all, right? It's very likely. And in this chance, it's essentially guaranteed to see data that is that extreme, right? But if we had something, if we had a data set here where we were comparing it to a population that had an average of 5, and I said, the average IMDb rating is 5, and I collected some data from a particular director, say, that had an average of 7.38, how likely do you think it is that 5 is different than 7.38? You're going to say those really do seem like different things. So we should expect a small p-value. And if we run this here, we'll see that that's in fact what we get. Now this p-value is in scientific or exponential notation. But if we want to see what this actually is, we can do this little scientific. You can see what that number corresponds to. So it's a very, very small number. And this makes sense. The more extreme your data gets from what you would expect, the less likely it is, right? So the smaller the p-value is, it's essentially telling you that your data is very weird. It's very different than what you would expect. So let's look at a different example here. So if we look at data 2, and again, we can just open this up in Excel to get a sense of what we're looking at here. We'll read it into R in a second. This data is a little bit of a different format. So here we have kind of the same idea. We have one column of values. So here we have a column for happiness, and then we have a column for gender. So it looks like we have, 25 males and 25 females. So here our research question is a little bit different. We're not going to compare, see whether this level of happiness is different than some known population level. What we really want to do here is understand, for this sample, is the average level of happiness for males different than the average level of females, right? So what we'll do is we'll read this into R. So I'm going to kind of do the same thing here. I'm going to call this data 2. I'm going to say read CSV. I'm going to say file choose. And when I run this, it's going to let me choose the file again. And this time I'm just going to choose data 2. And now I have data 2 here up at the top. And you see I have 50 observations and 2 values, or 2 columns, sorry. And I'll take a quick look at that. And again, this is the exact same thing we saw here. So again, we can visualize this data in some different ways. So let's just quickly do, say, data 2. And what we're going to do is make a plot here. And we're going to say what we want to plot on the x-axis is happiness. And we are going to say that we want to fill in the color by gender. And we're going to get a geome. Let's do a density plot. Let's see how this looks. That looks pretty good. We'll just change the alpha to something less than 1, so these become a little bit transparent. So what we have here is we can see that this sort of salmon color is the distribution for females. And you see that, a reasonable number of women in the sample had a happiness of 5, more had 6, and then it kind of trails off from there. Not too many people were a 10. For the male distribution, you kind of see the same idea, but they're mostly in this example, and again, fake example, most of the males said that they were a 7 out of 10 on happiness. So you can see that these distributions are a little bit different. They probably have different averages. And what we want to know are these differences different enough that we can't attribute it merely to chance? So let's also just summarize this data here. So what I'm going to do is just say group by gender, and I want the average happiness for each gender. And this is something that we've covered in the data manipulation workshop and in the data visualization workshop. But what this tells us here is that the average happiness for females in this sample was 6.88, and the average happiness for males was 6.6. So there's, inarguably a difference of 2.8. But what we want to know is, are these differences different enough that we wouldn't expect them to occur if males and females had the same level of happiness, right? And the way that we're going to do that is, again, with a t-test. So we can just write t-test. And we can write this out a little bit differently. So what we can do is we can say happiness is a function of gender. We'll talk about this in a second. I'll just type it out. So what we have here is this happiness, and we have this tilde, and then gender. And in statistical notation in R or other packages or languages or, statistical papers and that kind of thing, the way we read this is that what we're trying to model or understand or test is, does happiness change as a function of or because of gender? And then for data, we're using data too, right? If we were using a different data set, we would put that in here. So this allows us to use our variable names without that $sign, or they don't have to be quoted. So we can do things a little bit differently than we did up here, as long as we tell R what data set to use. So now I'm going to run this here. And again, we get some information here. The first thing I'll say, or maybe we'll come back to this later, but it reminds us of what type of test we're going to do. And I'll come back to this later. But down at the bottom, you'll see that it gives us that similar information as it did for the one sample t-test. So it reminds us of what the averages are for each of these groups. And this is something we calculated ourselves, but it tells us that the average for the female group was 6.88, and the average for the male group was 6.6. So again, of course, these are different numbers, but what we want to know is, are they statistically different, right? That is, if male and females had the same level of happiness in the population, how often would we see a difference this large or larger just by chance? And if we know how often it could occur by chance, then we know how to impress to be with the data we observed, right? So concretely here, we can look at this p-value, and what this tells us is, we would only expect to see a difference, a mean difference, in this case of 0.28. We would only expect to see a difference that big or bigger by chance about 40% of the time. So what that tells us is that's pretty probable, right? If there was no differences between male and females for happiness, we would expect to see differences this large or larger, almost half the time. So what that tells us is, we really shouldn't be impressed with the data we collected, right? We shouldn't really think that these two values, even though they're numerically different, they're not statistically different. So the interpretation there becomes, these two values, even though they're different, they're really not meaningfully different. So if we go back to that original illusions we were talking about, if we looked at the average in health for females and for males, even though those two bars are different heights, visually or numerically, statistically, they're really the same. So if this was something like a drug trial rather than males and females, even though those differences in health are different, what that tells us is the drug didn't have enough of a benefit for us really to think that there's a meaningful difference there. And this logic of p-value and significance testing takes a while to sort of wrap your mind around. But as we go through this, hopefully it will become more clear. And again, this gives us some other information like a t-value We won't go into what that means exactly because we'd have to kind of go into the mathematics. And then it also gives us a degrees of freedom. And we'll come back to this after I talk about one other thing. And then there's also these confidence intervals here. And the way to interpret these confidence intervals is essentially if we had one distribution of happiness and we sampled out these two different groups of males and females, then in 95% of these intervals, the true difference would be in those intervals, right? And that's kind of convoluted, but essentially the way to interpret these confidence intervals is in this case, because this confidence interval spans 0, because 0 is in between the lower bound and the upper bound, that tells us that this test was not significant. Or it tells us that we shouldn't really treat these two differences, these two values here as being different. So the confidence intervals and the p-value can tell you essentially the same information if you're using a cutoff of 0.05. And essentially what that means is in most research, what you're looking for is if this p-value is less than 0.05 or less than 5%. And what that would tell you is you would only observe this data by chance about 1 in 20 times if there were no true differences between males and females, right? And I use that in chance by quotes because there's sort of a lot that goes into that understanding of what chance means. But that's sort of maybe the colloquial way of understanding the p-value. So we'll keep going through here and we'll look at some other data sets. The one thing I'll quickly mention that I said I would come back to is you'll notice that here it ran something called a Welch's t-test. And there are really two different types of t-tests broadly that you can run. The first one is called a student's t-test. I'm going to quickly, I don't know why that doesn't show up there. So if we run the t-test with this flag here, or this argument called variance equals true, we'll see that our output will change slightly. And what it's going to run for us, it says a 2-sample t-test, but it's a student's t-test. And that's sort of the main t-test you would get if you're using SPSS or Excel or Stata or SAS or any of those programs. And really in that case, the variance or the standard deviation or the spread in each of your groups should be close. And there are tests to test for that. We won't really talk about that too much. But in cases where that's not true, what you can do is use this option here called var equals false. So if you have very large differences in the variances for each of your groups, so say your female group, spanned from 1 to 100, but your male group was all between 45 and 50, something like that. Those are very different variances. And in that case, you want to use something called a Welch's t-test. And you can do that by setting this variance equal to false. And when we run that, it'll give us this Welch's t-test. And you can see some of the numbers change slightly. So these p-values changed a little bit. The main thing you're going to notice is the difference in the degrees of freedom. The degrees of freedom, without getting into it, in this Welch's t-test is calculated by something called the Welch-Satterthwaite equation. But long story short, if your variances are different between your two groups, so if you visually observed that or you did a test to test that, you would want to use this variance equals set to false. And if I can quickly just make one argument, I would probably recommend, or I would recommend, always setting this to false. The Welch's t-test is just going to do a better job in every case, whether your data has equal variances or not. Through simulation and other things, you can prove that the Welch's t-test is superior to the student's t-test in making certain types of errors. So just by default, I would recommend always setting this to false, and you'll get this Welch's t-test. but things are interpreted the same. The p-value and the confidence interval and everything like that are interpreted the same. So that's basically it for the t-tests. So what I want to do is look at ANOVAs. Now, an ANOVA is very similar to a t-test. It really lets you just look at differences in averages. So say the differences in the average happiness for males and females. But the nice thing about it is it extends to when you have more than two groups. So here with the t-test, we had two groups. We had females and males, or you might have, a treatment group and a control group, or you might have people from Manitoba and people from Ontario. But when you have more than two groups, you need to use something called an ANOVA, and that's short for an analysis of variance. The thing I'll say about it is that you can use it also when you have only two groups. So maybe what we'll do here is we'll look at how to use an ANOVA when you have two groups, and we'll see that you get out essentially all the same information, and the critical things, the critical pieces of information like a p-value stay the same. So the function for using an ANOVA in R is AOV. And the nice thing is we can copy all of this and just save ourselves a lot of typing. So if I type in happiness as a function of gender, and I use data 2, if I run this, we'll get out some information, but it's not quite what we want. Most of the things you're interested in don't come here naturally. So what we're going to do is we're just going to stick this in another function called summary. And if we put that in this summary function, it's going to give us the information we want. So if we run that out, here is sort of the information you would expect to see in SPSS or Stata or anything like that. The first thing I'll just quickly mention is the p-value is the exact same as when we ran this student's t-test. So if I run this here and I run the ANOVA, we'll see that the p-value for this student's t-test was 0.42, and we get out the exact same p-value for the ANOVA. So when you have two groups, an ANOVA and a t-test are identical, and there's some other similarities too. Like if we take the t value and we square it, that's how we get our f value. So you can use R to kind of do some of the mathematical transformations to see how these tests are equivalent, but we're not going to really get into that here. But just like with the t-test, this p-value is interpreted the same way. We see that the way we interpret it is that the differences we observed in gender, we would expect to see those, again, by chance, about 42% of the time. So it's not, those differences aren't meaningful enough for us to think that the average level in happiness between males and females is different. Now, if that p-value is very, very small, and it could be if we had a larger sample size or if those differences in averages were further apart, that p-value is very, very small, like say 1%, then what we would say is that the data we observed, we would only expect to see data with that big of differences in averages about 1% of the time. And because that's so unlikely to happen by chance, we can feel pretty confident that those differences are real differences, right? And again, just to go back to this example, if we ran a statistical test here and we saw that these averages would only occur, or the p-value was only 1%, that would tell us that we could take these differences in averages seriously, right? They probably do represent truly different averages in health or happiness or whatever it was. But when we get a p-value of 40%, that tells us that we should probably treat these two bars as equal. So, without beating a dead horse, my main point is that there's a difference between those numeric differences and statistical differences. So that covers when you have just two groups, so we can look at t-tests or we can look at ANOVAs. Well, what about when we have more than two groups? So maybe we have, a group of people from Manitoba and Ontario and Saskatchewan, and we want to see if their happiness differs. Or maybe we have more variables. Maybe we have gender, but we also have a treatment group. And this is an example we actually worked through in the thinking with data, where we had, men and women, and a no treatment and treatment group, and then we look to see whether their health was different. Now here we can't use a t-test, either a 1-sample t-test or a 2-sample t-test. So this is where the ANOVA really shines. So what we're going to do here is we're going to read in data 4. I had to skip one part for data 3, but this file here we're looking at has all of the code that I'm typing out and some other stuff. So you'll have this available to you. So there's not anything that you'll be missing out. So here what we'll do is we'll say read CSV, and we'll say file.choose. And when we run that, we're just going to read in data 4. And I'll just type data 4 down here to get a look at it. And so what we have here is 3 different variables. So we have one for gender, female and male. We have one for treatment, people who didn't receive a treatment or people who did receive a treatment. And then we have their health. So what we really want to know is, within these 4 different groups, does the average level of health differ? Now, why did I say 4 different groups, right? And the reason why is because what we have here is every combination of gender and treatment. So we have females who did not receive the treatment and did receive the treatment. That's 2 different groups. And then we have males who did not receive the treatment and did receive the treatment. So we have these 4 different groups. And what we want to know is, are these averages different? And we'll look at exactly how we're doing that. But what we can do here is we can say data 4, and we can essentially do what we did before. We can group by, we'll group by gender and we'll group by treatment. And what we want to know is, what is the average difference? What is the average difference, or what is the average health for each of these groups? So we'll just say mean health. And here we go. So we can see that males who did not receive the treatment had the lowest health, and that was 5.2. And then the second lowest group, or the group with worst health in this made-up example, was males who did get the treatment, and so on and so forth, right? We could go through all of that. Now the question is, what we really want to know is there a difference between males and females, irrespective of treatment? And is there a difference in treatment, irrespective of gender, right? And one way we can get a bit of an intuition for that is just to plot this data, right? So if I say data 4, and I say, I'm going to just copy all this code. I'll just copy the whole thing, I guess. Copy this whole code. What we're going to do is just plot this little table we made here. So we'll say ggplot. On the x-axis, we're going to have gender. On the y-axis, we're going to have, maybe I'll save this to average health. So here I'm just saving this mean health as average health, just to make it a little easier to type. And then we're going to say we want to fill by treatment. And then we're going to make a column plot or a bar plot. And here we're going to do this. That's a bit of a refresher for the data visualization. But what this here gives us is, it shows us each one of these bars is an average for this group. So females who were not in the treatment group, females who were in the treatment group, males who were not in the treatment group, and males who were in the treatment group. And what we see here, if we just visually look at this, if we had to describe what we see, it seems like females in general have more health than males, right? And within each of those groups, it doesn't seem like there's a big difference, right? If we took the average for people who weren't in the treatment group, these 2 salmon colored bars, and compared that to the difference for people who did have treatment, those 2 averages would probably be about the same. They'd probably be somewhere around 6. And that's just by eyeballing it, but we could check that more formally. So what the t-test is going to do is, it's going to essentially allow us to do that. It's going to say, how big of a difference in health is there for gender? male versus female, and then how big of a difference is there for treatment, no treatment, or treatment. And the way that we're going to write that out is essentially the same as before. We're going to say summary, and then inside that, we're going to say AOV, and we're going to say that what we want to do is health as a function of gender plus treatment. And then data, we're going to be using data for. So what that tells us is the thing we're trying to understand is health, and we're trying to understand how it's different by gender and treatment. So if we run this, we're going to get out essentially what we did before with that one-way ANOVA, or the ANOVA only looking at one variable. And what we can see here is in this gender line, we get a very, very small p-value. And in fact, it gives us these three little stars here, which tells us it's somewhere between 0 and 0.001. So it's very, very small. So that tells us essentially that the differences in averages between males and females, irrespective of treatment, is different. And it's different in enough that it's statistically different. It's not only numerically different, but it's statistically different. Whereas for treatment, those differences are not really large enough for us to take them seriously, right? We would expect to see differences that large or larger close to 20% of the time, or 19% of the time in this example. And that fits in exactly with what we saw here. So we see, sure enough, right, numerically, all these bars might be differently, but the only thing that's statistically different is the group of females here and the group of males here. And I won't go through all of the examples, but data, let's see, data 4, 5, and 6 are all with the ANOVA. And we can, if you look at this, document that we'll pass around here, it shows some different examples and shows you how to measure those differences for either treatment or for gender. Now, the one thing I'll quickly show is that, and maybe what we'll do is we'll read in data 6 here, because this is a pretty important example. Final choose. I'm going to read in data 6. Now, this data is structured the exact same way as that data we were just working with. We have gender, treatment, and health. But the structure is a little bit different in terms of the results, even though the structure of the file is the same. So what I'm going to do is I'm going to copy all of this up here that we used for data 4. And I'm just going to switch out this for data 6 in those 3 places, and everything else will stay the same. So we can run this summary table here to see where the differences are, but the plot will probably be more instructive. And we went through an example like this in the Thinking with Data workshop, but it's good to go through it again and see how this translates to actually the output that you get from a statistical test. So here, again, we could visually look at this and try to make sense of the pattern of results. So if we looked and saw, is there a difference in average differences between females and males? Well, visually, the answer would be no, right? Because these 2 bars here are the same heights as these 2 bars here. It's just sort of mirrored. We could ask the same question for these 2 salmon colored bars. Are these 2 bars different than these 2 bluish bars? And again, the answer is no, they're just kind of flipped and mirrored. And yet there's a pattern of results here. And what this pattern of results is what they call an interaction. So the way to understand this data is to look at the differences in health for males and females individually while acknowledging treatment, right? So if you look at, for females, right, if we just look at these 2 bars, females, their health increased with this treatment, right? Females who didn't have the treatment had lower health, and when they had the treatment, their health increased, right? At least visually, numerically, right? We don't know about statistically, but at least looking at that, we can say that. But for males, they had the opposite pattern, right? So males had a higher level of health when they didn't have the treatment, and the treatment seemed to have made things worse for them, right? So there's a different pattern of results for males and females. And we could interpret the data in the same way by looking at the treatment, right? So if we looked at the treatment for males only, right, we could see that, you know, what we're doing is comparing this bar to this bar. So males who, if we're looking at within treatment, within treatment. So if we only look at treatment, people who had the treatment, right? This is the women who had the treatment, and this is the males who had the treatment. You can see that it had a positive effect on the women, but not the males. It's only looking at those two bluish bars. And then we could only look at the people who did not have the treatment. So this salmon colored bar and this salmon colored bars. And what we see is that within that, the females who did not get the treatment had lower health than the males who did have the treatment. So it had a positive effect not having the treatment for males for whatever reason in this fake data. But the main thing is that this treatment has a different effect on males versus females, or alternatively, the same way to think about it is that the treatment, the effectiveness of the treatment depends on whether you're male or female, right? And that's kind of a lot to wrap your head around, but again, I'd recommend, you know, drawing out something like this on a piece of paper and kind of making sense of that. Now, if we use this same ANOVA call here, what we're going to see is that this doesn't really get to what we're interested in, right? So we see for gender here, we get a large p-value, so there are no differences in gender. That checks out from what we saw in the plot. There are also no differences in treatment, which again, also checks out by what we're seeing. But what we want to do is be able to capture that idea of, well, is there an interaction? Is there some more complicated or nuanced understanding of the differences in health between these four groups that we can capture in the statistical test? And the short answer to that is yes. And the way that we do that, I'll just copy this below so we can see this, is we're going to change just one thing here. Rather than using a plus symbol, we're going to use a multiplication. And what that specifies in R is that we want to also look at interactions. So we want to look at exactly what we just talked about there. Does health differ within treatment depending upon your gender? Or does it differ within gender depending upon the treatment that you have? And if we run this, we'll see we get all the same information out, but we just get one extra piece of information. We get one extra rows, and that's this gender with a colon and treatment. And what that is the interaction term. And what we can see is that it's significant. And the way that we interpret that is that this interaction is much larger than you would ever see, again, by chance, right? I'm just going to use that in quotes without having to go through that whole explanation. So if we were interpreting this, the way we would interpret this is there are no differences in health looking at gender, irrespective of treatment. There are no differences in treatment, irrespective of gender, but there's an interaction between gender and treatment. So again, that is, there's a difference in health for gender depending upon your treatment, or there can be a difference in treatment depending upon your gender. So you really need those two variables together, gender and treatment, to make sense of how differences in health play out. If you only look at gender or you only look at treatment, there are no differences, but when you incorporate both of those variables together, there are differences. And again, this is something I encourage you to kind of play around with. Like I said, there are 3 data sets, data set 4 through 6, and this document here goes through all of that. And you can kind of start to build your intuition for where you would expect to see these differences in gender or treatment or that interaction. So the other 2 quick things we'll look at is correlation and linear models or linear regression. And I would say linear regression is sort of the workhorse of data science and statistics, because it allows you to do work with a lot of different types of variables. So here, you know, our variables were just groups with gender or treatment. But oftentimes you're interested in looking at things of like, you know, how often or how does the number of ice cream you eat influence how happy you are. And that was an example we worked through in the Thinking with Data workshop. But what we'll do here is read in data set 7. So I'm going to use the same idea, read CSV, file, choose, read it in data set 7. And if I just look at this down here, we can see that we have 2 numeric variables. We have ice cream and happiness. So what we could do is, we could make a quick plot of this just to take a look. ggplot, ice cream on the x-axis, happiness on the y. And we just want a point for each one of these rows. And that's what we get, right? And by looking at this, at least visually, it seems like there's some relationship, right? It seems like the more ice cream you eat, the happier you are, right? The couple people with the highest levels of happiness also ate the highest levels of ice cream. And the people who ate very little ice cream had the lowest levels of happiness. So what we want to do is, again, we know that there's some visual relationship, but what we want to know is this relationship structured enough that we wouldn't expect this to happen by chance, or we wouldn't expect this to happen if there was no relationship between ice cream and happiness in the population. So to do that, what we're going to do is use a function called core test. So just like with the t-test, we have t.test. With the correlation, we have core.test. And unfortunately, we're going to have to use this notation with this $sign here. So we're going to say we want data 7, and we want to use the ice cream variable, and then we're going to use this happiness variable here. So if we run that, we're going to get out similar information as with the t-test, and it's going to remind us here that we ran something called the Pearson correlation. This is just the standard correlation you would get if you used SPSS or Excel or anything like that. And it tells us what the correlation is down here. So if you remember, correlations always span from -1 to +1. And in this case, we have a strong positive or a large positive correlation, indicating that the more ice cream you eat, the happier you are. And that checks out what we're seeing in the plot. If it was negative, that would mean that the more ice cream you eat, the less happy you are. And then, of course, the thing that everyone is interested in is the p-value. And again, the p-value is small, less than 0.05 or 5%, which is that sort of standard cutoff for deciding whether something counts as significant or not. And given that it's so small, what that tells us is we would only expect to see a correlation this strong or stronger a very small percent of the time. What would that be? About 0.01% of the time, right? So it's very, very small. So the interpretation is that we can trust this correlation. This indicates that there probably is a correlation like this in the larger population. Now that's not quite accurate, but that's the way that most people would interpret this. The correct interpretation is, more strict interpretation is that if there were no differences, or if there was no relationship between ice cream and happiness in the population, we would only expect to see a correlation this extreme or more extreme this probability of the time. And that would include both the positive correlation, so anything greater than 0.75, as well as anything smaller than negative 0.75. And again, that kind of comes back to this idea we were talking about in the Thinking with Data presentation, right? This is the distribution of correlations you would expect to see if there were no relationship between ice cream and happiness. And the correlation we observed was very, very extreme. And it was so extreme that we would only expect to see a correlation this big, that probability of the time. So I know that's kind of a lot, but as you start to play around with these ideas more, or you start to analyze data more, that'll start to become a little bit more intuitive and make more sense. So the last data set we'll look at here is with regression. The nice thing is we can kind of take everything we learned here and use that for regression. So what I'm going to do here is use data set 8. Again, let's call it data 8, and then we'll say read CSV file, choose. And I'm going to read that in. And oops, I think I actually want data set 9. Sorry about that. Call that data set 9. Okay, so data 9, we can see that we have several different variables here. So we have an ice cream variable, number of hours watching TV, number of books read, gender, and happiness. So what we really want to do with this data is we want to understand how happiness is influenced by these 4 variables, right? So do males have higher happiness than females? We kind of looked at that with the t-tests and the ANOVA. But then we also want to incorporate some other variables that are numeric that we would use, that we could have used with something like a correlation. But here we have a combination of both numeric variables like ice cream and TV hours and the books that you've read, and gender, which is the category. And here is a good place for regression because it allows you to understand how a numeric variable like happiness changes over time, or sorry, not over time, how it changes or differs as a function of these 4 variables here. So let's look at how we actually go about doing this. Now, the nice thing is that we can, like I said, we can use what we know to use this linear regression model. So rather than using t-test or core test or ANOVA, when you're using linear regression, you're going to use this function LM, which is short for linear model. And then just like with the ANOVA, we're going to specify the formula for how we want to understand what variables we're trying to understand versus the ones we're trying to do the understanding, or to use the terms from statistics, right? What our dependent variable is versus what our independent variables are. And we'll talk about that in a second. So what we're going to say here is happiness is a function of, and I'm just going to copy these out here and put a plus in between these. And then I'm going to say data equals data 9. So this is our variable that we want to understand. We want to understand happiness and what contributes to it. And then everything to the right of this tilde, separated by pluses, are our independent variables. And those are the things that we theoretically are doing the explaining. We think that ice cream influences how happy you are, not the other way around, or the number of TV hours you watch, or the number of books you read, or your gender influences your happiness. That's sort of our idea. And each one of these rows is a different person. So this first person ate, this many pounds of ice cream in a year, or read this many books in a year, or sorry, watches this number of hours of TV a day and reads this number of books, and they were male, and this is their level of happiness. Now, of course, with this data, you would have to know how these variables were measured, but for our purposes, we'll assume that this is, pounds and hours per day and books per year and your gender, and then happiness on some sort of scale, right? So if we run this, just like with the ANOVA, we get out some information, but this isn't quite what we want. We want a more rich and detailed information than this. So I'm going to go ahead and just put that in the summary function. So now we have summary and then this linear model. And when we run this, we'll get out a more of a full report. So if we look at this, I'm just going to scroll up here so we can see what we have. I'll scroll up so you can see here. So the first thing we'll get is it just reminds us of the formula we used in this linear model call. So we know that already. And then it gives us some information. It gives us residuals. We'll come back to that. It gives us a lot of information about our predictor variables or independent variables, or the things that we want to do the predicting. So you see we have one row here for each of our independent variables. We'll come back to this in a second. And then in the bottom part here, we have a lot of information about this regression model in general. And we'll come back to all of these in more detail, but I just wanted to orient you to these main 4 parts. You have the call, you have something about residuals, you have a part about your different predictors, and then something to do with the whole model. That's just at a broad view. So let's take a look at this part here that says coefficients. So we'll see that we have, like I said, one row for each of the predictors we have. So ice cream, TV hours, and books. We're going to come back to this last one here because we see it looks a little bit funny. Rather than saying gender, it says gender male. We'll talk about that in a second. So the first column here we'll see is that it says estimate. And we see that for ice cream, we have an estimate of, let's call it 1. Now, the way that you interpret these estimates is that each time this variable increases by 1 unit, so in that case for us, I think we said it was pounds of ice cream a year. So each time in our data, the amount of ice cream someone eats increases by 1 pound, we expect their happiness to increase by 0.99 units. Now, of course, you need to know how that happiness was measured, but maybe an increase of 1 unit is meaningful, maybe it's not. It would, of course, depend on your data. But let's, 1 unit on a 10-point scale seems quite meaningful, right? So now what we can sort of infer from that is that if someone ate 2 more pounds of ice cream, their predicted amount of happiness would be 0.99 times 2, or about 2 units of happiness on that scale. Now for TV hours, we see that we can interpret this the exact same way, but we see there's a negative here. So the way we interpret this is that each time someone's number of TV hours per day goes up by 1, their expected level of happiness goes down because of the negative, goes down about 1 point on this scale. So, broad strokes, what we take from this is eating ice cream increases happiness, watching TV decreases happiness. And then for books, we see that it's also positive, but it's smaller. So here, each book you read only is expected to increase your happiness by about 1/10 of a point on this happiness scale. Now for the gender male, like I said, it doesn't just say gender, but it says gender male. And the way that we interpret this is that being male decreases your happiness by 0.08 units on that happiness scale. So in broad strokes, ice cream increases, TV decreases, books increases a little bit, being male decreases a little bit. Now, these last two might seem strange, right? They might seem like, why would books decrease or increase your happiness only by a little bit? And why would being male decrease your happiness by a little bit? And this is where we're going to look at this column here of the p-values. Now, these p-values are interpreted the same way. What it tells us, in a sense, is how seriously to take these estimates. So this estimate of 1 here, we can see that the p-value is very, very small. Again, it tells us that with these 3 little asterisks here, tells us that it's between 0 and 0.001. So what it tells us is that we can trust this value. Just like with a correlation, if you get a significant correlation, it means you can trust that correlation that you see. It's not a correlation that's likely to happen if there isn't actually a relationship between ice cream and happiness. Similarly with TV hours, we can trust this estimate here. But with books and mail, we see that these p-values are quite large. So what that tells us is that even though we have these values for these estimates, we can't trust these estimates. And really, we should think of these 2 estimates here as being no different than 0. So even though these values here we could think of as, we can kind of take them at face value, these ones we can't really say are any different than 0, statistically speaking. Of course, numerically speaking, they're different than 0. Anyone can see that. But statistically speaking, they're not any different than 0. Another really important part of regression I'll just mention is that, unlike with a correlation, when we look at the relationship between ice cream and happiness and get this estimate out, this regression model is holding all these other variables constant. So the true interpretation of this is that each time someone eats 1 pound of ice cream per day, their expected amount of happiness would be expected to increase by 1 point on this scale, holding all of these other things constant, right? So if there was something that, well, people who eat ice cream also watch more TV, and those two variables were related to each other, it's holding those two things constant so that ice cream and TV hours aren't conflated or sort of tangled up together, but it's looking at each one of those things by itself. And again, I kind of encourage you to play around. There's 2 data sets that are included, 9 and 10, that have regression. And it's good to visualize the data and play around and see if these numbers make sense. You should see that, this isn't always strictly true, but if you looked at the relationship between TV hours and happiness, you should see a negative relationship because this estimate is negative. But that can change a little bit in the regression model. The other things I'll quickly mention, we won't go into it too much, but the standard error is essentially a measurement very similar to the standard deviation. And what it's telling us is how trustworthy, in a sense, or how, maybe not trustworthy, but how accurate the measurement is for this estimate. So the smaller the standard error, the more confident we are in this estimate. And then the t-value, we won't go into the math, but it's essentially just the estimate divided by the standard error. That's how you get the t-value and the probability we already talked about. So that's how you interpret each of those values. You interpret them individually. You'll notice too that in this first row here, we have something that's called the intercept. And the first thing I'll say about it is that whether it's significant or not does not matter. That really just depends upon the scale of your data. Whether it is significant isn't really often of any interest. But what is of interest is the estimate. So here we see it's 5. And the way you interpret that is that is sort of the baseline level of happiness if all of these variables, so ice cream, TV hours, books, and gender, were either 0 or the default category. So to be concrete, your expected level of happiness from this data set is 5.13 if the number of ice creams you eat were 0, the number of TV you watched was 0, the books you read were 0, and your gender was female. And the reason why R decided to put gender male here is instead of gender female is it just does it by alphabetical order. And you could change that if you wanted to by doing some data manipulation, but for the most part, it's okay. If this said gender female, this estimate would stay the same. The only thing is it would be positive. This standard error would be the same. This t-value would be positive, but this p-value would be the same. So it doesn't really matter the order. It just would change your interpretation. Your interpretation there would be, if you were female, your expected happiness would go up 0.08, but it still would not be significant. So you would still interpret that as no different than 0. So I know there's kind of a lot going on there, but that's how you interpret really any regression model. You interpret those predictors, one predictor at a time, to understand whether they have a positive or negative effect. And then you want to look at the p-values to see whether those estimates can be said to actually be different from 0. And if that p-value is large, typically you wouldn't treat these values, like these last two, as being any different than 0, even though they're numerically different than 0. So I want to save some time for questions, but I want to go through this, this bottom part here. So this bottom part here is not looking at any particular predictor or independent variable. So it's not looking at ice cream or TV or anything like that. It's looking at your model as a whole. And sort of good interest to us, and we talked about this in the Thinking with Data workshop, is this R squared here, this multiple R squared. And the way that we interpret it in this case it's 0.74. The way we interpret that is that in all of these differences in happiness, each participant had a different level of happiness. Our model here accounts for 74% of those differences. And what that means sort of by consequence is that we understand 74% of what contributes to happiness in this data set, and we don't understand 26%. Now, this is a made-up data set. In the real world, you would rarely have an R-squared of 75 or 75% differences explained. But in this example, we do. We're able to explain a lot of what contributes to happiness from these few variables. Here, right next to it is something called the adjusted R-squared, and here you can see it's quite similar. And what the adjusted R-squared, it's interpreted in the exact same way. The only difference is that it adjusts the R-squared value for the number of predictors you have. So if you had 100 predictors, it would penalize you for needing so many predictors to explain happiness, whereas a model that could explain happiness with a handful of variables wouldn't have that penalized adjusted R-squared. But most of the time, if you have a reasonable number of predictors, those two values are going to be the exact same. And again, it just tells you what proportion of differences you can explain with your model. And again, it gives you some information on F statistic, degrees of freedom, that sort of stuff. We won't get into that too much. But what it also gives you is a p-value. And this p-value is for your model as a whole. So using these four variables here to understand happiness, do we understand happiness from this model, or do we model happiness from these four variables in a way that is significantly different than if there were no relationship between these four variables and happiness? And again, because it's very small, we interpret that as, yes, there is a difference, or sorry, not a difference. This model does attribute or does make sense of the data in a way that isn't attributable to just chance. Now, the last thing I'll quickly talk about here, which I said I'd come back to, is this residuals. And what this shows you is the difference in your actual level of happiness values in your data set and what the model predicts. So the model's worst prediction is about minimum actual minus predicted. I'm just thinking about this. So the residuals are your actual values minus your predicted values. So here the model is over predicting in the worst case, and it's off by about 2.26 points. So maybe someone, had an actual happiness value of 7, but this regression model thought they should have a 10, right? So it was off by about 2.5 points. In the other direction, maybe someone, again, had an average level of happiness of about 7, and the model predicted 9.64. So in that case, well, I think I'm getting it wrong, but it underpredicted in that case, at worst, about off by 2.6. Now, of course, you want these numbers to just be about as small as possible. The smaller they are, that tells you that your predicted values and your actual values are very similar. But you can see with this median here, the residuals, or the difference between the actual happiness values and your model's predicted values, the median value of that was only off by about 0.02. So that's a very small amount indeed, right? So that's sort of the thing you look at to get a sense of overall, how well is this model fitting? And this shows you sort of the most extreme cases, and these values show you the 25th and 75th percentiles. So there's kind of a lot to go in there. And again, this is only meant to really be introductory, so you get a sense of how to use these functions with R. But like I said, we'll make this document here available, which has everything that we typed out plus other things. So there were some things I skipped over, like this repeated measures t-test, just because we didn't have time. But everything we talked about here, including all the plots, all the summaries, all the tests, that's all included. And if you scroll down to the very bottom, or close to the bottom, there's a practice question here that sort of uses data set 10 to propose a data analysis question using linear regression, and has some questions that you should be able to answer based on what we talked about here. So, well, what is the R squared, right? You'd have to go and look in that output to see what it is, and what does that tell you? What are those slopes for the predictors, and what does that tell you? What are the p-values, and so on and so forth. But this has everything that we typed in more. And there's also a section here that uses a package called Broom, and I just didn't have time to go through this. It's not a sort of a core knowledge to have, but it's some nice to haves if you're building models with a lot of predictors and you want to visualize them. So there's this example here where you have all your different 50 predictors from your regression model here. You have your regression slope. So all these predictors had a negative slope and all these ones had a positive slope. And then there's some error bars on there, and then it shows you which of these variables are significantly different than 0. So sort of some tips or tricks if you're using a lot of predictors and you need ways of visualizing that, because this output can start to get pretty unwieldy once you have a lot of different predictors. So I would recommend, if you're doing a lot of regression modeling, to look at some of that to get a sense of some ways you can make your life a little bit easier in R. So I'll maybe stop there, and I'll take a look at the chat and see if there are any questions that I can quickly answer. Thank you very much. I'm just going to see here. Yeah, so this person asked, if you had a third variable, say age, could you use the ANOVA to find interactions? So the ANOVA will be just when you have a numeric dependent variable or a numeric variable that you're interested in understanding how that changes given some groups. And the ANOVA, you always are looking at within groups. So if you had, oh, I saw they said never mind there, but this is good to know. But when you have things like a combination of groups and numeric variables, there is where you'd want to use something like regression. And you'll, depending on your data, you'll see some very similar, or you'll see some very close similarities between the output of your regression models and your ANOVA models. And depending on the structure of your data, some of the values might even be the exact same. I'm just going to quickly look through here and see if there's any other questions. Okay. Okay, that actually might be all the questions. Let's see. Oh, how would you interpret the intercept? Oh yeah, perfect. Yeah, how would you interpret the intercept of the regression model? So yeah, that intercept is always going to be that if all of your predictor variables were 0, if they're numeric, or if they were the default category, so in our case, female, right, then that's what the expected level of happiness would be. I'm trying to think of another example there. And the one thing I'll mention too is that this intercept isn't always interpretable. So let's say you had something like, you were trying to figure out, you had a measurement of health and blood pressure, right? Your intercept for blood pressure could be 0, which would tell you that if someone had a blood pressure of 0, their health might be 5 units, however you measured that. And in that case, that isn't interpretable because, of course, you can't have a blood pressure of 0. There are things that you can do to make that intercept more interpretable. And one of them is to scale your data, to scale your predictors, so that each of them have basically take each one of your predictors and subtract off the mean of that predictor. And in that case, your intercept is going to be the average value. So rather than it being the value or the predicted value when that predictor is 0, it's going to be your expected value when your predictor is the average value. So again, with the health and blood pressure example, if you had a column for health and a column for blood pressure, and you took your blood pressure column and you subtracted off the average blood pressure, you would rescale that variable so that it had a mean of 0. And then when you put that in the regression model, what it's going to tell you is that that intercept, say it was 10, it tells you that when someone has an average level of blood pressure, whatever that is, their expected health is 10 units. And again, however you measure that. Now, someone also asked, can you include interactions in your LLM model? And you can. So you can do that the exact same way as with the ANOVA. You just put in the asterisk between the variables you want and we could, well, I won't do it now because we're getting close on time, but yeah, you can put that asterisk in, and that will allow you to have interactions between your variables, whether those are numeric or whether that's even like a numeric in a category, something like that. So you can look to see if something like, if there was an interaction between the amount males and females read on health, you could certainly do things like that. This person asks what caveat one should be aware of about the population distribution which the sample is drawn before using any statistical test. So yeah, these, and we didn't have time to get into it, but all of these tests have certain assumptions along with them, right? One of them, for example, is that, these data points that you're collecting are sort of randomly sampled from the population, right? If I was interested in health and I collected some data, by calling people rather than in a more random sample way. Maybe the people with phones have a different health than people who don't have phones. Or, if I went to the mall and had people fill out a survey, maybe the people at a mall have different characteristics for how much TV they watch or how many books they read than the general population. So anytime you're using these methods to make inferences about the population, you need to make sure, as this person pointed out, that your sample is representative of that population. And of course, there are some other assumptions that these tests have as well, such as things that, each of these rows in your data set are independent. So if you collected a whole bunch of data and you collected a whole bunch of data from one person, that likely wouldn't be a case where you're wanting to use something like linear regression. You might need to use other methods like linear mixed effects analysis that let you account for the fact that you might have repeated measurements from one person. And yeah, there's another question here about normality. And again, that kind of comes down to some of these assumptions about the tests. For tests like an ANOVA or for linear regression, your residuals are supposed to be normally distributed. So you could use some of these methods that we talked about in data manipulation or data visualization workshop to make sure that those residuals are normally distributed. Or to, if you're doing a one sample t-test, to make sure that that data is normally distributed. So yeah, these are all great questions. I think that's it for the questions, and we're right at 2:30. Yeah, the one question I'll just quickly answer because I just see it as, could we flip these variables around to understand ice cream consumption as opposed to happiness, right? So could we put ice cream as the dependent variable and some of those other variables as the independent variable? And the answer is yes. As long as it made conceptual sense, and this, a lot of this too will come down to this idea of whether you're trying or you're inferring any sort of causality. Things might be related, but they might not necessarily cause how much ice cream someone eats. But certainly, depending on what you want to understand in the data, in one instance, the variable might be the independent variable or the predictor, and in another instance, it might be the dependent variable or the outcome variable or the thing you're trying to predict. But yeah, I just want to thank everyone for attending. You know, we really only got to sort of brush the surface or scratch the surface of stats in R, but hopefully this gives you a bit of guidance into how to get started. And by using these stats method along with visualization and some manipulation methods, you can really start to build your intuition. And hopefully by playing around with some of these data sets that we didn't have time for today, you'll start to get a sense of how you can use statistics as a tool to understand data. So thank you very much.